we're going to look at some more techniques that we can use to prove identities. So the first type of identities we're going to look at in this particular video are sum and difference identities. And we're going to be using the unit circle, and we're going to be using all of those special angles that we learned. So the 45, the 30, the 60, we're going to use those special angles and the unit circles to help us prove the sum and difference identities. So here are your sum and difference identities. So first we have cosine of alpha plus beta. So these are just two different angles. So cosine of an angle plus an angle is equal to cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. Then you have the difference. So cosine of an angle minus the second angle is equal to cosine of the first angle times cosine of the second angle plus sine of the first angle sine of the second times sine of the second angle. Then you have your sine sum and difference. So the sine sum is sine of an angle plus a second angle equals sine of the first angle times cosine of the second angle plus cosine of the second angle times cosine of the first angle times sine of the second angle. And then the sine difference identity says that sine of an angle minus the second angle is going to be sine of the first angle times cosine of the second angle minus cosine of the first angle times sine of the second angle. So remember, this little angle here, it's alpha. It looks like a little fish. That's going to be the first angle. And then this angle here looks like a B. We call it beta, and that's always going to be the second angle. All right, so this is how we use the sum and difference identities. We use them to find exact values of sines and cosines of certain angles. So essentially, if you can take the number that they gave you for the angle, and we can rewrite it as a sum of two special angles, then we can find the exact value of that angle, of the original angle that they gave us. So for example, let's say we want to find the exact value of sine of negative 15 degrees. Now, negative 15 is not one of our special angles. It's not. However, negative 15 is the same as saying 45 minus 60. So negative 15 is the same as saying 45 minus 60. And 45 and 60 are both special angles. So we're going to rewrite sine of negative 15 as sine of 45 minus 60. So again, I rewrote the angle that they gave us, and I wrote it as a sum or a difference. In this case, it's a difference of two angles that are special angles, which is our 45, 60, and 30. And this one happens, the combination is 45 minus 60 to get negative 15. Now I have rewritten as a difference, I can use the difference identity for sine. So remember, the difference identity for sine says sine of your first angle minus your second angle. So sine of 45 minus 60 is equal to sine of your alpha cosine beta minus cosine alpha sine beta. So remember, 45 will be your alpha and 60 will be your beta. Okay, so we'll plug that information in. So again, I'm plugging in 45 for alpha, and I'm plugging in 60 for beta. Okay, so now once I've done that, I know all of these special angles, and I know all the trig values for these special angles. So sine of 45 is the square root of 2 over 2. Cosine of 60 is 1/2. Minus cosine of 45 is the square root of 2 over 2. Sine of 60 is the square root of 3 over 2. So I replaced all of these with our special exact values that we know, our unit circle. And so after that, all I have to do is simplify. So I have the square root of 2 over 2 times 1 over 2, which becomes the square root of 2 over 4. And then I have the square root of 2 over 2 times the square root of 3 over 2, which becomes the square root of 6 over 4. And then I can just rewrite, since the denominator is the same, I can rewrite that as one fraction, the square root of 2 minus the square root of 6 over 4. So this is the exact value of sine of negative 15 degrees. All right, now our next type of identities that we want to look at are called the double angle identities. So these can be proved from the sum and difference identities, and this is when the angle that they give you is actually 2 or double one of our special angles. So if they give you an angle and you know, oh, that angle is the same as saying twice the amount of a special angle, then you can use the double angle identity. So this is the double angle identity for cosine. It's saying cosine 2 times a special angle, so 2 times alpha, is equal to cosine of that special angle plus the special angle. And then sine 2 theta, or sine of 2 times the special angle, is equal to sine of that special angle plus that special angle. And then, of course, this right here, cosine alpha plus alpha and sine alpha plus alpha, then you can use the sum identities to take that further. Okay, so let's go ahead and expand that. So cosine 2 theta, or cosine 2 alpha, after we apply the sum identity for cosine 2 alpha, we end up with cosine squared alpha minus sine squared alpha. And then, which is the same as saying 1 minus 2 sine squared alpha, which is the same as saying 2 cosine squared alpha minus 1. And then now we have our sine double angle, which is saying that 2 sine alpha times cosine alpha. So this is what we get after we applied the sum identity to that sine alpha plus alpha. So this is how we can use the double angle formulas. Let's say we want to find the exact value of cosine 90. So 90 is not 30, 60, 45. However, 90 is double of 45. So that means that I can use cosine 2 alpha, where alpha is going to be 45. So I'm going to use the double angle identity for cosine, which says that cosine 2 alpha is equal to 2 cosine squared alpha minus 1. So this is the identity that we're going to want to use, okay? And remember, alpha is going to be 45 because 2 times 45 is 90. Okay, go ahead and plug in that information. So I'm plugging in 45 for alpha, and then cosine of 45 is the square root of 2 over 2. So I'll go ahead and replace that cosine 45 with the square root of 2 over 2. Cosine is being squared though, so I'm going to go ahead and square both of that, so that becomes 1 over 2. And then I still have this times 2 right here. So 2 times 1/2 it just becomes 1. And then 1 minus 1 is 0. Also, factoring can be useful when you're trying to prove identities. If you factor it first, then you can set each of those things equal to 0 and then solve for your missing value. To see an example of that, if you look at example 3 on page 471, you can see how factoring can be used to prove identities. Another thing that's useful is multiplying by the conjugate. So sometimes if you have a denominator, if you multiply by the conjugate of your denominator, things will simplify and cancel out, and you will be able to prove your identity. To see an example of that, look on page 471 and look at example 4.